This video is going to cover section 5.3, which is going to talk about two new tests, the divergence test and the integral test. And when I say tests, what we're testing is we're testing whether or not a series, like what we talked about in the last section, remember a series is the sum of an infinite sequence. What we're going to do is test whether different series converge or diverge. And we'll talk about later why that's important. But we need to know, depending on what a series looks like, whether it converges or diverges. You'll also remember in the last section we talked about a specific series. We talked about the geometric series and how to tell if that type of series converged or diverged. We also talked about the harmonic series, and we discussed the fact that the harmonic series always diverges. And so now we're going to take a look at a few new tests. One of those tests, again, is the divergence test, and the other is the integral test. And then the last thing we're going to look at is another type of common series that we're going to see a lot, and that's the p-series. And it's really easy to tell if a p-series converges or diverges. So in this video, let's jump right into the divergence test, and we'll read what it says. It says in Theorem 5.8, it says the divergence test. It says if the limit of our a sub n as n approaches infinity is equal to c. C is some constant. This is a constant. And that constant is not equal to 0. That's important. Or, so it's two things. If it's equal to some constant, or if that limit does not exist, d n e, in either case, then the series diverges. Notice one thing it does not say anything about convergence. This never proves convergence. Okay, now this is a really simple idea here, and I just want to touch it. I mean, to understand how this test works, it's really important to understand what's going on. So let's just make a little side note here. Remember, a series looks like the form, we have something that goes from n equals 1 to infinity of some sequence. So we're adding up the infinite terms in a sequence. And so it looks like a1 plus a2 plus a3 plus ... And so there's an infinite number of terms. And so what this is saying is, let's say the terms of this sequence start to approach something. So let's take for an example, let's say our sequence, let's say a sub n looks like this. Let's say it looks like 1/2, 3/4, 5/6, 7/8, 15/16, and so on. All right, so it looks like those terms are approaching what value? What are they getting closer and closer to? Well, it appears that the limit of, and I don't know what the formula, we didn't go over the formula, but just the concept here, it looks like the limit of this, of a sub n, is equal to 1, right? So that means eventually the terms in this sequence are approaching 1. Well, what that means is if we take a look at the series, if we go from n equals 1 to infinity of this a sub n, then we have 1/2 plus 3/4 plus 5/6 plus 7/8 plus ... And eventually, because all the terms are approaching 1, we just basically keep adding 1 every time. Plus 1, plus 1, plus 1, plus 1, plus 1, and so on. So if we just if all the terms in the sequence are approaching 1 and we just keep adding 1 to our sum as we add more and more terms, is this sum ever going to add up to something, right? Are we ever going to get a sum, a finite sum? And the answer is no, because we just keep adding 1, right? If you have your sum is 57 and you add another term of one, and then you get 58. If you add another term, you get 59. If you add another one, you get 60, and so on. It's never going to add up to some finite value. In other words, it diverges. And so this fits with the divergence test. Because our limit of our terms was some constant other than 0, it's going to diverge. All right, so let's take a look at example 1 here. It's on using the divergence test, and it says determine if the series is divergent or convergent. Well, it's actually a typo here because we don't really know enough yet to tell if it's convergent. Remember, this theorem never proves convergence, so we're not going to tell that, and we're not going to find its sum. So sometimes this test is going to be inconclusive. So we just want to determine if it is divergent. So let's jump in here. Okay, so all we do is we take the limit as n approaches infinity of n squared over 5n squared plus 4. That's all we do. And because we have n squared on the top and n squared on the bottom, those are the same powers of n. Then we know, I mean, we could do L'Hopital's rule, but we should know from limits that this will reduce to 1/5. And remember, what we're doing is we're saying, okay, is that a constant that's not 0? Well, it is. This is not equal to 0. So that means eventually, no matter what the terms of the sequence are, we start adding 1/5 every time. It's never going to add up to something. So what's our conclusion? Our conclusion is that it diverges, right? So our series, n squared over 5n squared plus 4, diverges by the divergence test. And it's so important that you understand how simple this is. So let's just use this as an example real quick. So this sum, n equals 1 to infinity of n squared over 5n squared plus 4. What does that say? Well, the first term in this sequence, this is going to be what? 1 squared over 5 plus 4 over 9. Next term is 2 squared is 4, 5 over 24, plus, and we keep going, and eventually, because all the terms in the sequence are approaching what? All the terms in the sequence are approaching 1/5, right? Since all the terms in the sequence are approaching 1/5, eventually, we just keep adding 1/5 every time. Well, if we keep adding 1/5 as we add terms to our sum, is this ever going to approach something? And the answer is no. It's going to be infinity. It's going to diverge. So that sum is going to approach infinity. The series diverges. Okay, let's do one more. So this next one, again, we're going to do the same thing. We're going to take the limit as n approaches infinity of e to the 1 over n squared. And if you plug in infinity for n, this is e to the 1 over infinity. Remember, 1 over infinity is 0, so this is e to the 0. This is 1. This is some constant other than 0. So what can we say about the series? We can say it diverges. So n equals 1 to infinity, e to the 1 over n squared diverges by the divergence test. And it's very important that you get in the habit, as we start learning all these different tests through the rest of this chapter, it's very important that at the end of a problem, you always state your result and you state why. You have to prove why it is the case. You can't just say it diverges. You need to say it diverges why. You need to explain why. So, and I will do that on all the examples we cover in this class. All right, that's going to do it for this video. In the next video, we're going to talk about the integral test. Thank you.